We're talking about physical modeling from first principles today. And yeah, we've been talking about so far various ways of emulating physical sounds or made up sounds rather than building up from first principles. So today we're going to talk about going the other direction, which is start from physics and build your way up to what the sound should sound like. I'm going to start with an inspirational clip from Carl Sagan here.
If you wish to make an apple pie from scratch, you must first invent the universe. Thank you very much.
All right, so that's what we're going to do. So we're going to have to start from first principles, of which there's many different ways to do it. All right, so here's the pros and cons I was going to ask you, but I think we'll just go through it. So physical simulation of sound. Note, like most of the methods that we have covered so far made up the bulk majority, 99% of sound synthesis up through the late 80s. Obviously, by the time we get to the 90s, you start seeing heavier and heavier use of sampling. But at about the same time, you did start to see more and more emphasis on trying to physically model instruments themselves. At this point in time, if you look at commercial virtual instruments, the majority are sample based, but you're starting to see more and more that are physical modeling based and also more and more that are neural. So in terms of simulation versus emulation, pros of simulating from physics, the biggest one is that you have immense control. If you understand the physical system from first principles, you can tweak it to have very, very large amounts of control. You also get a fundamental understanding, so you know why things are behaving certain ways in theory. And sometimes it might be computationally advantageous. It depends on your method. A lot of the stuff that we're actually going to talk about today, at the time that it was invented, was at the limits of what was computationally tractable. But that means older methods, and actually Ange talks about this. Older methods can actually be pretty computationally efficient, or even real time. And these can be validated, because you know how the model works. You can check things like, does it preserve energy? Does it do the right things? Cons, it's really, really freaking hard. Like a lot of these methods, really quickly, you're getting into like really hard physics, maybe across multiple disciplines. Every technique is like a new invention. So like a lot of these things have nothing to do with each other, besides maybe modeling the wave equation. And it's possibly not necessary, right? Like at this point, we have like 7 or 8 different methods that produce very high quality sound. If we add the neural stuff that we're going to be doing in a week, that's yet another. And so, but they're really interesting, and there's a pretty wide range. It typically looks something like this. You have some mechanical vibrating system that you model, maybe just with a sine wave, or maybe emulating the wave equation. And then you have it mechanically coupling to additional systems that start to distort or shape the sound to sound like the timbre of an instrument or a physical system like a voice. Then it's going to, there's going to be some sort of acoustic coupling. Maybe you skip the step entirely and just sample from like the instrument baseboard, kind of like you would do with a pickup on a guitar. But maybe you actually model the waves going through the air. We're going to see examples of that. So that would, come from the Navier-Stokes equation. And then finally, there might be some sort of acoustic transformation, so reverb or echo or some sort of room transfer function. But this is generally the pipeline that you see for all physical modeling, these 4 steps. So for instance, if you were modeling a guitar, you might start with the vibration of the string. There's different ways to do that, which we're going to talk about. And we've already talked about some methods for simulating the string or emulating a string, but for simulating, we're talking about today. And then you might look at the guitar soundbox vibrations that couple to the string, which vastly transforms the timbre. And then you might look at the sound propagation from the sound hole, and then finally maybe room resonance or room effect. So like, initially you might start with like the wave equation, then work to maybe some sort of finite element method or some sort of discretized form of this guitar body. You also can just use knowledge about what the nodes are for the guitar in that case. Then you might potentially move to computational fluid dynamics. More commonly, it's useful if you're modeling maybe a wind instrument, but you could also apply it to any system that's making sound, obviously. And then finally, you might apply some sort of additional reverb or room effect. That, more likely than not, is something you're not physically modeling, but you can, and it is modeled physically. All right, we're going to start with strings. So, Phoebe, you already talked about strings a little bit, right? You talked about what their harmonics look like. I'm just going to go into a little bit more depth about how you would model an individual string. So this is from a PDE book or PDE presentation, but if you look at any PDE book, it's going to have this derivation, or any book on sound. So Thomas Rossing's book on sound or Walter Strauss's book on PDEs, both are great derivations of this. But basically you're looking at a small linearized perturbation on a string. The string has some sort of tension, which is a force per meter. And then you're also going to have some sort of density of the string, which is some sort of gram per meter. And or so the tension is just a force, right? So you have a tension force in the string, and then you have an energy per unit length. And from that, assuming a small perturbation, you can, and you obviously treat sine as approximately x, you're able to get to something that looks like this, which is the wave equation. And this is actually often used to motivate the wave equation, like in Strauss's book, for instance, as probably one of the easier systems to model and get to the wave equation. In earlier Gridspace IAP lectures, I actually derived the wave equation for sound. And if you want to find that, that's actually from 2 years ago. But if you go through this and you find the solutions to the wave equation, you see that you have basically two solutions translating in one direction and the other direction at the speed c, which is the speed of sound in that material. In the case of a vibrating string, it's the square root of the tension force divided by the mass per unit length. And if you do the unit analysis of that, that's a velocity, right? And that's the wave speed. And so, like, for instance, if you consider I pluck it at as a diagonal or triangular pluck, you're going to get two different traveling waves in either direction. So this is like an infinitely long string. If we bind the string, like Phoebe talked about in her lecture, you could solve that by pinning the two ends of a finite length string. And in any PDE, if you have containment, you tend to have quantized solutions. So in this case, this would be different nodes of vibration or modes of vibration. You typically solve that with something called separation of variables, which if you study PDEs or quantum mechanics, is kind of the easiest way to approach PDEs. It just means you assume that there's some sort of space-dependent solution, which would be the different quantized waves. And then there's some sort of time-dependent solution, which is the vibration speed for that node. So that would be a way that you could simulate and prove that a contained wave, like on a guitar, is going to have these nodes, which and the ratio of those nodes that you saw, like in the additive synth lecture and also the subtractive synth lecture, you can actually solve through Fourier methods by assuming some sort of initial pluck and then find what is the relative excitement of the different nodes. And you'll find that where you pluck the string, that's why when you play like a harmonic on a guitar, which I was going to do, but I'm not going to do, if you play it right near the center, where you're mostly exciting the first mode, it's going to sound like a sine wave, but as you move closer and closer to the edge, you're more and more exciting the additional harmonics. What that means is the timbre of the instrument isn't just dependent on the instrument itself, but how it's plucked. And if you actually just take the Fourier coefficients of that plucking and then solve the wave equation for each coefficient, you're going to see how each of those individual plucks travel and how much of the modes it's going to excite. Any questions so far from anyone here? Okay, cool. Here's what the solutions look like for the different harmonics. We kind of a rehash of what Phoebe showed. These are called the Chladni patterns. I always have trouble pronouncing it. The way these are normally found is they excite an instrument, and then using laser interferometry, they can find where the nodes where it doesn't vibrate. So just like the string has these nodes, there's also two-dimensional nodes. There tends to be two quantized numbers instead of one. So you have the 0, 0, the 0, 1, 1, 0. And whether it's a drum head or a guitar or even like a vibrating tube, you tend to see these patterns, and they have different frequencies. And these are found experimentally, but they tend to map onto what like a drum head looks like. It's just they're distorted by the special shape of the instrument. And so if you want to model the timbre of the guitar, you start with a guitar string, but when it couples to the baseboard, which is actually the mechanical amplifier, you need to know kind of the shape and frequencies of the board. But notice that these nodes have frequencies that are different than the modes of the string. and they're actually independent of the string being played. So the string is going to sympathetically couple to this other resonator that has completely different modes. And so you have one resonating system coupled to another. They have different frequencies. If you play something that's close to the resonance of one of these frequencies, you're going to excite that node more directly. And in general, if you ever watch how guitars are made, like acoustic or classical guitars, they actually put very carefully layers of mass inside the guitar, and the luthier, which is a person who makes a guitar, will actually excite it with strings and then listen to how it resonates until these nodes are classically, placed. Same goes for if a luthier is making a violin. They're going to look for these patterns to resonate with certain notes on the instrument. This is an example of someone then simulating that full system in SolidWorks. I don't think they're doing any fluid dynamics here. This is just a finite element solution. What that means is they're modeling little triangles of mass. So for both the string, which they know is steel, and then for the body, which they know is wood, which is a relatively easy thing to do in SolidWorks if you import these models and then say what materials they are. And this is what you get. Sounds pretty damn good to me. And that's just from pure physics. This is a commercial VST, an instrument plugin for modeling different types of strings. This one has a lot of parameters and can make string instruments that are very vanilla up to ones that are very exotic. I'm just going to play this for a minute or doing here, if you look at the parameters, they have multiple strings that you can change the anharmonicity and the harmonics of, and then they have properties of the strings themselves, the mass and the stiffness, which was the T and rho that we saw earlier, other way around. And then you can change things about all the effects that are being played on it, which are in this case not really physical effects, I don't think. All right, we're going to talk about pipes. So again, a review from Phoebe's lecture. There's closed and open pipes. How does that matter from the perspective of partial differential equations? Lokman, do you know? No? Do you remember the different types of boundary conditions in PDEs? What are they called? One of them is a French guy, that's right. So there's different boundary conditions. So when we pinned two ends of a string, when we solve that by separation of variables, we basically require that the spatial solution is 0 at both ends. And that's what results in like a sine, where you start at 0, end at 0, and then various other frequencies of sines. In this case, you can notice you've pinned it at 0 at one end, but on the right side, it's actually at its maximum. And what you typically have in PDEs, when we have that guitar string, that's called the Dirichlet boundary condition. I assume that's what you're talking about. And that's where we basically require that the solution is 0 at one end and solution at the other end, 0 at the other end. With an open pipe, instead you're requiring that the first derivative is 0 at the end. That's called the Neumann boundary condition. Or you can have a mixed boundary condition where it's Dirichlet at one end and Neumann at the other, and that's how you get a closed pipe like this. So otherwise, it's the same wave equation, except you're modeling sound waves, which again, 2 IAPs ago, I derived that equation, but it's same sound wave equation with a different speed of sound. So you can just look up speed of sound for error, and that'll give you what you need to do. In reality, the effective pipe length of something like a clarinet or a flute is slightly longer than the actual length of the pipe, and that's due to the bell that are on different instruments. And so for a flute, it's pretty close to this, but for like for clarinet or bassoon, the bells have an effect on that. There's also Robin boundary conditions, but have nothing to do with this lecture. Okay, cool. Any questions about pipes? I thought I had examples, but it doesn't matter. I have plenty of other pipes later. No? All right. So this is called carpless strong synthesis. This is one of the two most common traditional methods for physical-based simulation. Like a lot of the stuff in this class, like FM synthesis last lecture, Carpless and Strong created this at Karma. I think Carpless is now at UC Santa Cruz, I'm going to say. This is an algorithm for simulating mostly originally string instruments. And the idea is to physically simulate it, but in a way that's pretty computationally tractable, which is from the form of Z transforms, which I think Natalie talked about. So the algorithm is pretty simple. You have a noise source, and then you take it, you feed it into a delay, put that delay into a filter, and then feed that back in. And so this results in pretty reliable string sounds. The reason being, so imagine if you hammer a string, you have an initial burst of noise. You just have this initial noise sound, and then eventually it resonates. So if you remember, when you have feedback in a filter, that has a resonance. And so there's a natural resonance to this filter. So if you remember, actually, when Nico was showing the multi-pole filter on his subtractive synth, he was able to get it to generate a sine wave. Remember, he's like, there's your sine wave. That's because he was hitting one of the poles as a multi-pole filter and then getting it to resonate. So in this case, you have a filter with a decay in it, so that eventually that feedback dies out. Adding decay to feedback also broadens it a little bit, just like the decay in a string is going to cause it to not be perfectly resonant. So it sounds like this. This has been around for a while now. So this is actually a modular synth that it just does that form of synthesis. They kind of sound a little bit robotic to me, but it was like a very early form of string synthesis. I think you could actually probably often get better results from other methods at the time, but it was physically based, although only kind of loosely. So that brings us to digital waveguide synthesis, also invented at Stanford, and it was kind of inspired by that method. But the idea was, instead of just having one impulse and then a resonant filter, is have many different sub-resonators. So if you, let's say, wanted to model a trumpet or a trombone, where you have different chambers that all have different resonances, or even just a Helmholtz oscillator blowing over a bottle, it looks a little bit like that string synthesis, except you're exciting it, maybe not with a noise impulse, but with like some sort of continuous sine wave. And then you have a network of resonators. So this allowed actually pretty sophisticated physical modeling of resonant and brass instruments. And they actually tend to sound really good. And so here's an example of one of these. This is from Julius Smith's Karma page. So he was creator of this method. So this actually, got licensed to instrument companies just like FM Synth by Karma at Stanford. But the idea is that you typically often have, so in this case, you have the reed, in this case, some sort of scatterer, and then multiple bores or multiple resonant chambers, and then a bell. But you can actually have really, really complicated networks of resonators. And that's just by combining these same filter systems, similar to when Uche was showing how you could combine multiple subunits of operators for FM synthesis. In this case, you're combining essentially multiple versions of the last method to build this out. So this is an example of a software that is emulating maybe a basic flute, where you have, again, an initial resonator, then additional resonators in the pipe, and then a bell. And he's changing parameters here. Any questions on these last two methods? Yes, you seem like you're about that.
That sound where you visibly, not visibly, audibly hear the delay almost. That's the delay in it getting to the resonant.
Yeah. There's a delay in the feedback loop, and then there is a low pass filter, and then that feeds back. Oh yeah. So the question is that delay sound you hear the delay sound in the filter? And the answer is it is, yeah. Do people understand these last two methods? These were for many years the most commonly used in physical-based modeling. So basically that first unit, you have, some excitation, maybe noise, and then a feedback loop where you delay it, and then you low pass filter it, and then it resonates with some decay. And then if you combine a sequence of these, you can start to simulate more complex instruments like brass or woodwind instruments. And this method is also heavily used in early speech synthesis experiments, but I don't want to spoil any of that stuff. Yep.
Each resonator has just it's like the singular resonant frequency, and then you're building up multiple resonators to build up tower.
Yeah, classically. Oh yeah, so the question is you have multiple chambers with their own resonant frequency, and you're combining the resonators to build up timbre. And yeah, that's exactly what you're doing. And so that's exactly how like brass instrument works. There's just these multiple resonating cavities. And just like a Helmholtz oscillator, where you have maybe an excitatory area and then a reservoir, and then you're compressing the reservoir and then exciting the top resonator. But if you continue to add holes, you can kind of emulate that really easily with this. That said, I think this method was so widely experimented with and adopted. I think there's like more complicated filters and more complicated networks, but they all kind of were derived from that original method. Cool. This was the first commercial example that Yamaha made. Again, Yamaha licensed this technology, I believe, like they did with FM synthesis. This was a really, really expensive synthesizer. It was like 10 grand when it came out. They later made other synths that used this method. It sounded pretty good at the time. This is from the late 80s, maybe a few years after the DX7 that we saw last week. I do not know anyone with a VL1, but if you do, let me know. So it was like pretty amazing. And they were really, really rare and expensive. I think when they came out, it was really not until the 90s that these methods became more readily available. But like the adoption has never been that high, actually. I think really now is probably the peak of adoption of a lot of these methods. Cool, drum heads. So back to Strauss differential equations. This is near the end of the book. So if you contain a circular membrane and apply Dirichlet boundary conditions, then you have a drum head, like a timpani or snare drum. And so, like I mentioned, when you have a two-dimensional vibrator, you tend to have two quantum numbers. And in the case of a circular drum head, we get a bunch of Bessel functions. If you remember from Uche's last lecture, he also talked about Bessel functions that come up in the spectrum of FM synthesis. Probably not a coincidence. And so that's how you solve just an ordinary spherical drum head if you solve the quantum numbers of spherical drum head and then approximate something like the back of a guitar, by putting it through some sort of transfer function or distortion or just approximating it as an ellipse, you can reuse those solutions to kind of eyeball what the nodes will be for any two-dimensional membrane, which is often kind of how they name the nodes in these patterns that they find through laser interferometry. I also have a picture of this is, again, this is from Thomas Rossing, who I learned acoustics from. And but his book Science of Sound has a lot of these pictures. This is on the side actually of a snare drum, and you can see again they look like little vessel functions basically. So here's an example of drum synthesis using this method, basically directly from the PDEs. But he also, I think maybe in this one emulates a snare. By the way, you can see he's adding room effect like in my diagram here as well. So setting what the resonance is, or the reverb rather. All right, we're going to talk about brass. So brass instruments are among the types of instruments most commonly physically modeled. In general, in the last 15 years, both sample-based and physical-based models for brass instruments have gotten really good. I could probably show hundreds of really cool examples that are on the market. The first few things I'm going to show are two commercially available brass instruments from the same company, and then we're going to show Ange's trumpet model as well. Their same trombone. And here's Ange's take, where actually, in his case, instead of modeling it using tricks, he actually models it from first principles using the Euler equations for flow. Entirely real time, including the visualizations. All right. Any questions on that? Cool.
We don't have questions. We do have a just want to say that this is
Ange, we have your best work coming up, or at least he requested that we show his latest engine work and his steam engine generator. So we're gonna have that later in it for your request. But Ange, thank you for joining. You want to ask Ange? Do you have any corrections or anything you want me to add? Otherwise. And it's on a delay, so. Well, if you do, just put it in the chat and Nick will let me know. All right, we're going to talk about other physical systems. So about 10 years ago, there was a really large swarm of SIGGRAPH papers on sound synthesis. So if you're not familiar, SIGGRAPH is like the largest conference for graphics. It's often where a lot of the research that later makes its way into like the game industry and in Hollywood originates. And I follow a lot of these papers pretty closely just because it's an interest of mine. And obviously, neural methods have kind of taken the center stage, but a lot of these methods are actually incredibly high fidelity. So this is from 2016. This is focused on a frequency domain method for simulating bubbles, source of sound.
Fluid sounds come mainly from bubbles. When a bubble is formed, it's forced into volume oscillations, giving off pressure waves that we hear as sound, like this. In slow motion, we can see the sound is radiated as the bubble forms. The volume oscillations of a bubble can be modeled as a damped harmonic oscillator, i.e. a spring. The internal gas of the bubble and the surface tension at its wall provide the...
Sorry, I just have to say this. There's a really famous book that for people that are preparing like for their quals in physics that was produced by University of Chicago, and it's a lot of like back of the envelope physics questions. Familiar with that book, Lookman? It's a great book. Anyway, it's like I love back of the envelope physics, but one of their classic problems is deriving from just units what the vibration is for a bubble underwater. But anyway, sorry.
The restoring force, while the surrounding liquid is the mass. The frequency of the oscillator, omega, depends on the stiffness and the mass. We show how to compute the mass term more accurately than in previous work.
A follow-up work that was a time domain method.
Fluid sounds
could actually be applied to a large number of systems, including bubbles. And some of these, this is from 2018, some of these results are incredible. Nonlinear thin shells and music. All right, so this is another sound synthesis model. This is a SIGGRAPH paper from 2016 on crumpling. So they'd model basically the system as a mechanical system and then just sample the sound from that.
Its synthesis of plausible synchronized soundtracks for physics-based
Sorry.
for sliding and contact events and crumpling events. We use concatenative sound synthesis. We derive our parametric friction model by recording and analyzing the following experiment. Clip from a data-dimensional feature
Is similar to parametric speech synthesis, where they sample a bunch of sounds in the real world and then take some sort of linear combination of them based on parameters of the cloth simulator. Cloth simulators, you typically have like an array of like a 2D array
Present a
of
practical data-driven
vibrators that are connected by springs of different stiffness. And you typically have like orthogonal ones and then diagonal ones, and that determines the properties of the cloth. And then they just basically sample that to get the audio. So this is a fracturing paper from SIGGRAPH 2020. Here's fire. All right. I mean, all those actually pretty effectively show if you wanted to use any of the other synthesis methods that we've seen so far, you'd either have to experiment pretty much indefinitely to just have to discover that sound. I mean, a lot of these involve like turbulent flow and all kinds of other complicated effects. And then if you wanted to correlate it to a physical object, like they're doing in a lot of these SIGGRAPH papers, you also then need to figure out some sort of way to tie the other simulation to whatever other synthesis method you used. The classical solution in like video games, which Ange, you talk about, is just essentially play sound samples, which for things like a driving game or things like a game where you have rigid body dynamics or fractures would be like hard to do well without doing something like this, which is still fairly rare. So I'm going to take a little bit of a detour. The next thing is not technically from first principles sound synthesis. It's instead an example of, you guys have heard of false color pictures. So here, this is on the left, a false color image of infrared photography of the same person. And that allows you to see, as if something were in the visual spectrum, something that you otherwise would not be able to see. Leverages the visual system so that you can see things as if your eyes were able to do that, right? Sonification is like visualization for sound. It's really useful when you have time domain signals where that have a lot of structure that you have a hard time really appreciating without listening to. Again, personal interest of mine is sonification. I was able to think of like 9 examples that I liked that I put together here. But it also shows you how you can pull, like we were doing with granular synthesis, you can pull sounds from nature and then use them as the basis for something else. In this case, these are collected from various scientific studies and missions. The first one this is one that I've actually wanted to do myself for years and probably will at some point. These are called whistlers. So in general, when there's lightning, it generates a radio impulse, and you can pick these up with a radio antenna. And in general, the ionosphere transmits different frequencies of radio at different speeds. So you have what's called dispersion, similar to what you see in like a prism for light. And so as a result, certain frequencies arrive first and other frequencies arrive later. If you ever like twanged a big metal cable like they did to get the blaster sounds in Star Wars, that's that same effect where you basically see different sounds arrive at different times. And so they sound like this. And these have been found, this is on Earth, but they also have been found on Jupiter, or sorry, on Venus, I mean. And so there's lightning on Venus, and you can listen to it just like that. Next one is from LIGO. So this is from one of the first set of, I think this is neutron stars combining. Do you remember, Lookman? It was like a pair of neutron stars. I think later on they found the neutron stars combining with black holes. But this is actually the sound that they picked up. So if you're not familiar, LIGO has 2 recording stations, one in Louisiana, one in Washington. They use laser interferometry to find very, very small changes in physical space, very similar actually to the laser interferometry that we use to get those guitar patterns earlier. And then they can turn that into a time domain signal and play it in the audio band. It sounds like that, why it starts at a low frequency and goes up. The opposite of the whistlers in this case is that as they decay, as the orbiting system loses energy through gravitational radiation, the radius gets smaller, which counterintuitively maybe causes them to spin faster, which causes the gravitational radiation to increase in frequency. And gravitational radiation obviously is pretty different than sound. It's polarized like light, except it has 2 types of polarization, so it's very weird, but you can still play it as intensity in the audio band. This one is pulsars. So pulsars are high intensity radio generators that are spinning, and you can hear every time they briefly align with Earth, you can hear a click. The next one, so these are Cassini collected radio emissions from Saturn and Enceladus, and these are often called the songs of Saturn. We also have similar data from Jupiter that I'm not playing today. This is sun sonification. So this is actually of the turbulence in the atmosphere of the sun, kind of like earthquakes. This is what a black hole sounds like. This is fairly recent. So this is just direct radio data of black holes. This is of the cosmic microwave background radiation, and actually you probably have listened to this before, not this exact, the way they did this is pretty unique, but like if you are picking up just like static on an old TV or radio, some of that energy actually might be from the CMB because you have this background of radio. So obviously originally this was a very high frequency bit of radiation, but as the universe expanded, it stretched out to the microwave, but you can still listen to it. It sounds like this. Cosmology, like the spectral structure of the CMB, actually carries a lot of information about the early universe, but it also kind of cool. Last one, this is the sound of an earthquake from, obviously you can just take the seismometer data and play it, and this is multiple seismometers in Japan in 2011. I think this is pretty fucking cool, actually. All right. Yeah, I know, it's cool as hell, isn't it? That's my favorite one. I wanted to do the Whistlers thing for years. Maybe this is the year. All right, we're gonna end with the grand finale, Ange, your stuff. So engines I think are a really interesting choice of system that Ange looks into, because there's a lot going on in it. So there's, depending on how you decide to model an engine, and Ange, you lamented that, in general, engines are pretty central to the experience of someone playing like maybe a driving game, but also someone who maybe like actually wants to diagnose a problem in an engine or like many other reasons. But there's so much going on, right? It's like the centerpiece of, the whole field is called engineering because originally that was like what we had. And so, you have Newtonian dynamics, you have thermodynamics and fluid mechanics. So both fluid mechanics, for the sound itself, but also for things like compressible flow. And then he's also doing visualization. And in Ange's videos, he does all different types of visualization, from particle effects to different coloring schemes to distorting pipes mechanically to help visualize things. And this is all, he's targeting real time and it has to sound good. And so we're very lucky. Ange, thank you again. He sat down with us earlier, and we're going to just play some of that discussion about his work. But first, we're going to actually just look at a little bit of your... so if you're not familiar with Ange's work, so he has a YouTube channel where he simulates everything from engines to that trumpet that we saw earlier. His engine simulators are really cool and like really like he's kind of a wonderkind. And on top of that, he has a game on Steam, which is the perfect place to buy it because it's a Steam engine simulator if you've ever seen it on Steam. And he also has some videos about the development of that game and the continued development of that game. But this is one of, I think, your most recent video, Ange, where you're showing your engine simulator. So I'm going to skip. We'll skip.
Hey, what's up guys? Today we're testing out some multi-cylinder engines and making performance optimization. From an audio perspective, single-cylinder configurations are probably the most difficult to simulate convincingly. There's less room for manually tampering with the sound or massaging the output audio to get a desired effect. My logic was, if the simulation can simulate one-cylinder engine sounds passably, it should definitely be able to do larger engines. Well, today we're going to be putting this theory to the test. I'm going to be writing this code in the ES3D prototype application, which I've been using as a testbed for simulation development. We can take the 4-stroke single-cylinder demonstration and duplicate it a few times using a bunch of for loops. The code quality in this prototype is not that great, so for loops spammed all over the place doesn't even look that bad. Now let's listen to this very approximate demo that I put together in New Engine Simulator. Junctions are not supported yet, so I couldn't model the exhaust system exactly. These are technically called zoomies, and it's basically just saying that every cylinder has its own exhaust system. Anyway, this is not how most engines are in real life, so just keep that in mind. Even though I was not able to replicate the actual parameters of the engine, I think it's pretty clear that this is a major improvement from old Engine Simulator. In my opinion though, the end result is not actually the biggest achievement here, but rather how that sound was created. Old Engine Simulator is too coarse to meaningfully simulate most types of resonance and acoustics. To make up for this, it uses some light audio processing to try to recover some of the lost higher frequencies. Unfortunately, these synthetic frequencies don't have a strong basis in physical reality, so they end up sounding out of place sometimes, like the incessant static that I talked about earlier. If we disable all of this audio
Any questions, or did
The shape of an object is simulate the sound. Somebody studied the inverse problem for the sound. Guess what the shape.
Oh, that's an interesting question. So the question is, a lot of these methods start with some sort of geometry or shape and then figure out the sound from that. Has anyone looked at the inverse problem of start with the sound and figure out the shape? If I had to guess, a lot of people who work on submarines have worked on that problem, but otherwise I don't know. But one thing I actually also meant to put in this lecture that I just forgot to put in is there's actually, so if you're familiar with the synth world, if we figured out anything in the last week, there's a big community of people that care a lot about sound. They range from people that are, playing around with Ableton Live and plugins to people that have, 50-year-old hardware filled with plugs and wires. There is a large affection for analog synthesizers, especially because they were among the first that we talked about. But even like noise engineering, I think they only make one analog synth. Analog electronics is hard. It's hard to make reliable. It's hard to build. It's hard to design. And also there's a large demand for old electronic instruments that use analog components that are impossible to maintain. And so there's a large number of plugins and simulators that actually emulate analog electronics to emulate specifically Moog synthesizers, for instance. And they're emulating like the temperature dependence on passive components like resistors and capacitors. They're emulating how these things detune as they warm up. And so there's a pretty large amount of physical simulation of electronics to emulate old, mostly subtractive modular synths that themselves were trying to mimic instruments in the real world. So it's kind of life imitating art. Cool. Well, if there aren't any other questions, sorry for skipping the best part, didn't mean to. I think we're going to jump into our Q&A. Thanks everyone. Put your hands together for Ange. Thank you.
Again, I first learned about you through my co-founder Nico. We're both big fans of graphics and real-time simulations and obviously audio technology. We first saw your early work, just first principles making engine simulations. Could you maybe just for us and just for everyone who's going to be watching, talk a little bit about your background and how you got started?
Sure, yeah. So, originally my background doesn't really have anything to do with what I do now, so it's not really relevant. I worked in investment banking for a while. That was mainly in like derivative pricing and stuff. And then after that, I worked at Amazon. I worked in Amazon Alexa. And then I worked at Google for a bit. And that was around the time when I created Engine Simulator. And yeah, so my background in the tech industry is pretty standard. It doesn't really have anything to do with sound synthesis. The way that I got into sound synthesis is a little bit strange. So basically, I started working on a project car. I think it was, I don't know, it was a few years ago, and it ended up like costing a lot of money. So I wanted to figure out a way of taking all of the knowledge that I gained in that and actually turning it into something that was useful for my career. And this was the closest way that I could think to do it. And yeah, I don't know. I wasn't really expecting anything to come out of it. And it was a lot more successful on YouTube than I was expecting. And now I guess it's my job. And that's how we got here.
What do you think is it that draws people to seeing you kind of build these simulations, and what do you think makes it exciting to people?
I think that there is, I think there's a lot of elements to it because I've always been interested in simulations, and I always found that the simulations that you typically get in video games are, I don't know, there's something missing about them. And I'm not really sure how to explain it exactly. Like, there's obviously something there, and a lot of them do have some utility, but I don't, it doesn't feel right for some reason. Like, you can kind of tell, like in a game, if you're interacting with, let's say, an engine or some kind of machine, you can tell that the approximation is very simplistic. And I always wanted a bit more than that. And I think that a lot of people have a very similar experience, and that is especially relevant in car games. This is probably the one genre where the audio design has not evolved that much in a very long time. I mean, the graphics have come a long way. The physics are really advanced now, but the audio is still it's advanced a little bit, but at a much slower pace than everything else. And it just so happens that that is a critical component of the car driving experience for most people. As, you know, childish as that sounds, people like the sound of engines, and if that's missing in the game, that's like a important feature of the vehicle that's not there anymore. So by adding that and making it feel like, you know, it's like a real engine that responds like you're used to in real life, I think that that excites people about the possibility of potentially having that in racing video games. Um, and I think that's probably like the main element of it, at least in the context of engine simulations.
In general, like, I mean, having done, fluid simulations, one of the hardest problems is they tend to be, they're a system of nonlinear differential equations. They tend to be very tricky from the like numeric stability perspective. What
Yeah.
sort of issues have you dealt with in terms of like numeric stability?
Yeah, I mean that is a problem because in my simulations, most of the literature that I'm following, they describe, and I've talked to like also some of the authors of those papers, they usually talk about simulations in the sense of, okay, I set up this simulation with, you know, very specific parameters. I'm going to leave it to simulate a time slice of like, I don't know, a few seconds, a few minutes or whatever. They leave it run overnight, then they check the results like the next day or whatever. That's like a typical use case that I've seen for this kind of simulation. But the simulation that I'm working on doesn't work like that. You have to, it should be able to continue running for hours at a time without having any of these numerical instabilities just completely blow up the simulation. And this was a problem because the first time that I ran the simulation to generate audio, the more recent one that I've been working on, it just blew up instantly. So it's like, yeah, it really doesn't want to exist most of the time, but I found that like there are certain what's it called again? There are certain techniques that you can use that I think make it a little bit better. And these have also been known, like there are like flux limiters and stuff like that, which I use in the simulation. Some of them work better than others. A lot of it, actually, one of the craziest things that I learned about fluid simulations is there's a surprising amount of almost subjectivity that goes into them, which you wouldn't necessarily think would be the case. Like, and I thought I was crazy because I was reading through the literature and trying to understand, you know, why is it that there are different flux limiters for different like wouldn't it just all be the same thing? But
Yeah.
apparently not. And the way that one CFD expert put it to me is he said, there are many ways to skin a cat. With his words, it's obviously like a kind of old-fashioned phrase now, but basically what he means is that there's just multiple ways of doing the same thing, which seems really weird to me because like wouldn't there just be one way to do it if it's supposed to be a scientific simulation? But yeah, apparently there is some degree of subjectivity and sort of like massaging that goes into making a successful fluid simulation. And in my case, I'm not necessarily bound by being scientifically rigorous. So I can, you know, add certain approximations where I think is necessary. I can add certain code that will prevent the simulation from blowing up, even if it's not, you know, completely scientifically sound. The exact scientific output of my software is not that important. So, yeah, it's like, I don't know, it's a lot of trial and error and using techniques that have been used for a long time to prevent instability like that, and also just making sure that the simulation is always running within the boundary that will mostly ensure that it's stable, but even then you're still not guaranteed. So yeah, it's complicated. I haven't even like fully solved that problem myself. My simulations still blow up sometimes, so I don't know.
Grounded in the real world? Like what's like what for you, like how important is that and how do you do it?
A lot of like, I think the easiest way to check is energy conservation is probably like the first check that I would do anytime that I'm doing a simulation of any kind. Because if you're not conserving energy, something's not right. I mean, that's just the instantaneous red flag there. So there are some like theoretical checks that I do like that. In terms of grounding it to real life, I think it's a little bit easier for engines because like I built an engine in real life, I tested it, and I know all of like the power figures and what the general effect of installing certain things in engines is. And that was kind of how I calibrated the original engine simulator. I basically looked at like for example, the volumetric efficiency with respect to the engine speed. This is a very it's not predictable exactly, but it follows a curve that is pretty common among a lot of engines. And if you're simulating it and it doesn't follow that curve, then probably something is wrong. So yeah, there's quite a lot of information available for engines, also in the research literature as well, which I use to kind of cross-check the output of the simulation. And ultimately, because I'm trying to make something that appeals to people that are interested in engines, the most important thing was when I make an engine, when I replicate a real world engine in the simulator and I run the engine on a dynamometer, does it match the results in real life? So that was really like and that's obviously a test of like the entire system as a whole. It doesn't really test any one thing in particular. And yeah, that was kind of like the most important sanity check that I did. And it worked out to be like not that inaccurate. I mean, for a tool that makes audio, the fact that it gave pretty accurate horsepower numbers for a lot of different engines that I tried was kind of crazy. And that was actually I think that was one of the main catalysts for the success, the initial success of that application is that it wasn't just people interested in video games that liked the program. It was also people that worked with engines in real life because they tried the program and they could see for themselves that the numbers actually matched what they saw in real life. And they ended up seeing maybe there's some utility in this pertaining to my actual job. So yeah, that was probably the main thing in terms of engines that I used.
Have you ever like thought about like learning more about like machine learning and trying to apply it to, maybe fill in the gap between your simulation and, a real engine or have you ever, have you like learned anything about like machine learning?
Yeah, it's been a common like suggestion in my comments section where people think that you could take
I'm glad I've been elevated to YouTube.
Yeah, well, I mean, you're maybe a little bit above a armchair physicist in my comments section, which there are a lot of them. Um, but yeah, this it's an interesting idea. I don't know that much about machine learning myself. I did apply actually a very simplified machine learning type technique. This was so long ago that it's not like new in my mind, so I can't like explain it that clearly, but essentially what it is it's like a predictive model. So I use this on Steam Engine Simulator. So essentially you have your stream of audio data that's coming out and you have a predictive model that basically just learns from I don't know, the previous like 200 samples or so. I don't remember, a few hundred samples. And because it is kind of common that you'll have a situation where like you'll have a little bit of lag or something like that, and then you miss the next window for generating samples, it will just generate a few samples to fill in that gap. And then so basically you go from just zeros, which doesn't sound very good, and just sounds like popping and clicking. So you go from that to it sounds like a bit of a bit rate reduction, like nothing that most people are going to have too much of an issue with. Most people don't even notice it. So yeah, that's probably the furthest that I've gotten down the AI rabbit hole. Like it's a little bit of like linear like nothing crazy, like not like a neural net or anything like that. I guess you could consider it to be like a very primitive neural net, I guess, in the sense that
I get that a lot
the
too.
yeah, but nothing, yeah, nothing crazy.
Yeah, there's like two common ways that I think people will often use neural networks for things like this. One, there's something called like physics aware neural networks where like the fundamental physics, and then you have some ground truth data of the actual physical system. And instead of trying to predict everything with a neural network, you just try to predict the gap,
Yeah.
the perturbation. So like an example that I've always really liked is you can just try to have a neural network predict uh the dynamics of a drone, but then it has to like learn about lift and has to learn about Newtonian dynamics, but and it tends to perform pretty poorly at if this is like to use a neural network for a flight controller. But instead what
Mhm.
you can do is give it the predictions from like Newtonian dynamics and the lift equation, and then just try to predict the delta. And that's really good for like things that are really nonlinear, like ground effect when it's close to the ground. And there's all, if you like look up physics aware neural networks, that's a big area. And for sound, it would probably work great. Because you could obviously just have it try to predict, from your starting point. The other thing that people often use it for is distillation, which is, you have the ability to, given like, your engine parameters, generate a lot of audio. You can then use that to generate all the training data you want to try to, just build a model for your own model. And that can be, that's mostly interesting if you want something that's less computationally intensive, but still produces, similar results as distillation. So those are both fun ones to look up.
Yeah, there was another like suggestion that I've gotten a few times is to basically take the output of the simulation and then use that as training data.
Yeah.
Because it'd obviously be like pretty difficult to get that training data in real life, but I mean the simulation can just run constantly and just generate whatever you want. Um, it would also be interesting, like now that you mention it, so the way that most physics engines work, or at least the way that the physical simulation that I use works, it can benefit a lot if you pass in a rough estimate of what the answer is actually supposed to be. And this is how a lot of them work. Like you basically take the output from the previous frame and you feed that in as kind of like a hint. I guess the best way to think about it would be like having a better starting point if you're doing there's I forget what the name of it is. It's like basically if you pass in a good starting point to like gradient descent or something like that, it ends up converging to the solution faster. So that could potentially be interesting if you had like a physical simulation with a bunch of constraints and you have almost like, because I can imagine myself, if I'm watching it, I can probably make some rudimentary predictions about where the best values probably will lie. And then you can maybe feed that in, maybe improve the calculations that way. I'm not sure, but yeah, could be interesting to try at some point. Actually, I just thought of one question that I do have. I get this comment a lot. Uh, People ask, is it possible to take, because they see in my videos like, oh, there are these tubes and they're like, making sounds. And their question is, can you use that to simulate basically like a human vocal tract? Now, I've seen various ways of doing this that don't exactly use like a CFD, but it's kind of like physically modeling those or that structure. I'm just curious, like, is that actually on the horizon for synthesis, or is it just more efficient to use, like, I mean, AI can already generate voices pretty decently. Is there even any room for that kind of simulation?
Yeah, so I think I have a pretty good answer on that, but yeah, Phoebe and Natalie jump in. So one, they've been doing physical simulations like that for many decades. I mean, they've been trying for 50, 60 years to build the good physical models of the larynx and how it's manipulated by the transfer function of the mouth and teeth and everything. And there's even been physical simulations that have been built, which I think we'll probably show a video of in our class. Um, And they can be pretty good at generating like formants and like vowel sounds and voiced sounds, where it really starts to break down. Even really modern attempts to do this, just completely from physical modeling, is as opposed to something like an engine sound, it really gets into the uncanny valley, where we have a
Right.
really high sensitivity to fidelity when it comes to speech synthesis. So even like earlier other methods of speech synthesis that were actually like pretty intelligent, that use like triphones and these like parametric methods that were like very sophisticated, they always sounded like very, off to us.
Yeah.
And even now with neural methods, we still struggle with what's called prosody, with how it sounds relative to how someone would emphasize a word or exactly how they would do it. Neural networks are really good about learning these little subtle details that help with the uncanny valley. And there's also just the data itself. When you're modeling from real microphone data, it's not going to just reproduce the person's voice, but the transfer function of the room, the transfer function of the microphone, puffs of air going into the microphone, and a lot of these subtle details that aren't like you're not maybe completely conscious of help sell that it's real, because it's not just that it's real, that you've really modeled with the neural network the larynx really well, or dental frictives really well. It's that it's also modeling sound of a person talking conversationally. So that includes things like intonation and how they break up words, and then also all these physical effects. And so a lot of these, just like the ground effect on the drone, there's all these weird nonlinear things that you would just never have the time or even thought to put into your simulation. Whereas with machine learning, it makes its way in, which is like one reason why physics-aware neural networks might be interesting for you, because you can generate an engine sound. You can probably very easily put it, add reverb and make it sound like your engine's in a giant, garage. But if you
Yeah.
want to actually, cover these like last couple little effects, like maybe the way that a piston rings or something, I don't know, like you might actually be able to, capture that little bit of extra fidelity. The thing is, it might not be appreciated with an engine or in an animate system in the same way it is with basically voices, hands, and faces, right? People are just super attuned to it. And so that stuff is super uncanny valley, risk. And so that fidelity bar is just incredibly high. And that's actually one of the things that we do that's different than other folks and have done for years, is we mostly record conversational speech. And we also record it on a microphone that's realistic for someone talking on the phone. And even that stuff makes a big difference. I don't know. I mean, Phoebe, there's other stuff too, right?
Yeah, the other main thing I'd add to that is just sequential dependence, like the way you say a specific word at different parts of a sentence, dependent on what words have come before it, words are coming after it, is extremely hard to physically model without an insane amount of modeling it differently for like a million different combinations of sentences.
Yeah.
And that kind of sequential dependence and exactly. And that's something else that neural nets are just kind of better at modeling sequential dependence based on data. And also you don't have to think specifically about why you change how you're intoning something, which
Right.
you know, very good at describing why they say things differently either. So having something that can just learn that from the data without us, it just sounds more natural.
Right. Makes sense. Yeah, I mean, now that you mention it, it makes sense that certain tiny details would be more appropriate, or would probably be better handled by a neural network as opposed to a physical simulation, because it usually is those areas where approximations have been inserted, I think is where a lot of the uncanny valleyness can arise. So it'd be interesting because I noticed also in fluid simulations, the flux limiters and stuff like that I was talking about earlier, it really seems like when they were designed, they are an incredibly primitive way of processing the data in a way that a scientist reviewing the data, or a human observing the data, would massage the data so that it continues to make sense. So it would be interesting if you had an AI overseer that could manage that and still retain a lot of the detail that you don't want to miss in the simulation. Because like if you just smooth it out completely in the hopes of keeping it numerically stable, that's not good because then your audio doesn't sound good anymore. But if you had a way of preserving that detail, that could potentially also be interesting. But I don't know. I don't know. I don't know too much about the AI stuff, to be honest. But it is something that would be interesting to look into at some point.
Well, I mean, I know you love computers, so you'll love it.
Yeah.
We're really big on computers here too, so honor to meet you, fan forever, and have a good evening.
All right. Well, thank you, and you guys have a good evening as well.
Well, Ange, thank you for joining if you're still on the stream. And thank you everyone else from MIT and Gridspace here today. Up next, we are going to be moving from sound to speech. And like we just covered, speech is its own animal because it's the one thing where you have to kind of be perfect. And it's got a 60-year history that we're going to start on Wednesday. And we are going to have some early pioneers in speech synthesis, just like we did in music synthesis, and other special treats and guests. So we're really looking forward to it. It's something that I think Gridspace is best in the world at. And so we're excited to share that with you all.
Singing in purely physical terms is essentially a matter of pitch and timing. In the next selection, the computer sings a familiar ditty. Daisy, Daisy, give me your answer too. I'm half crazy, all for the love of you. It won't be a stylish marriage, I can't afford a carriage, but you look sweet upon the seat of a bicycle built for two. The computer now sings the same tune, but to a musical accompaniment played by another computer. Piano students will notice that the music-producing computer has a rather stylized left hand. Incidentally, synthesizing music on a computer is almost as formidable as making a computer talk.